Okay, a box plot is a graph that allows us to identify the position of chunks of data, and it's broken up by percentiles. And so a box plot, generally, drawing a box plot, is a graph that looks like this. You have a box in the middle, and then inside the box somewhere, you're going to have another vertical line, and then you're going to have this tail off to the left and a tail off to the right. This is what you're after. And it's just a one-dimensional graph. So all you need is a scale that is uniform, and this graph can be at any height above the horizontal scale. So here would be a box plot. Now it's all based on 5 numbers, and those 5 numbers are the minimum value, the smallest data value in the entire set, and then you've got the largest data value in the set, and then this number right here is the median. So we looked at yesterday how to calculate the median, the middle data value, and we would call this the 50th percentile. 50% of the data fall less than the median, 50% of the data fall above the median. It's the one right in the middle. Now to find these guys, these are called quartiles, Q1 and Q3. Q1 is the first quartile, and a quartile is a percentile, but it's a 25 percentile. So there are 5 of them. The minimum is like the 0th quartile, and then you've got Q1, which is the first quartile, and then the second quartile is the median, and then the 3rd quartile, and then the 4th quartile is the maximum. So there's those quartiles. Q3 is the 3rd quartile. Our graphing calculator can construct those 5 numbers. I mean, in fact, it prints them out right in order in your output screen. So we're going to plot the min, the Q1, the median, the Q3, and then the max. And if you take those 5 numbers from a data set and draw a graph like this, it's called the box plot. Sometimes it's called a box and whiskers plot, because you have the box and then some whiskers. But this is a pretty standard graph that we use when we're going to compare a single set of numerical data. And it's another one that you're going to see in the homework. All right, let me give you an example, and then we'll do it in 2 different ways. I don't want a really big data set, but all right, well, here's one. Okay, so for this data set, what they did is they looked at Keebler cookies and store brand. And I don't know about you, but I noticed the store brand, they usually don't have as many chocolate chips, or their chocolate chips are smaller. So Keebler, or some of the other brand names, they do a pretty good job with chocolate chips. So the question is, we're going to draw one box plot of this guy, the Keebler number of, all right, so what is this? To find out, a student randomly selected 21 cookies, and then they counted the number of chocolate chips, 32 chocolate chips in that cookie, 23 in that one, 28 and so on. So these represent the number of chocolate chips in 21 cookies. So what we're going to do is we're going to draw side-by-side box plots, and we're going to have one for Keebler, and we're going to have one for the store brand, and then we're going to plot them together so we can see if all the data together indicates that one cookie is more superior than the other. All right, now, whenever we have a larger data set like this, we're always going to punch it into the calculator and let the calculator do most of the work for us. So what I'd like you to do is to enter in the data. We're going to put the Keebler data in L1, and let's put the store brand data in L2. And there's a lot of data values there, but they're just 2-digit numbers, so it's not going to take you a lot of time to enter in all these data values. And again, I don't need to remind you that even though the data up here in 3 columns here, we're not going to put it in L1, L2, and L3. We're going to put all 21 of these in L1. I highlight my last data value. I see that it's in position 21. I'll scroll through the rest of them just to make sure that they're all 2-digit numbers. All right, and then come down here and then put in the store brand in the next one. All right, I'm going to show you now how to calculate the what we call the 5-number summary. The 5-number summary is a listing of those 5 numbers, and they all appear in your calculator on the second page of output when you run the one variable statistics command. So number 1, you need to enter the data, and then number 2, remember we're going to go to the stat menu, and then we're going to calculate. Go to the calculate menu, and then option number 1 is the one variable statistics. It gives you lots of summary statistics related to our single variable. And in this case, it means chocolate chips. All right, now we have 2 lists, so we're going to have to repeat this twice. So we'll write down the 5-number summary for the Keebler cookies, and then we'll write down the 5-number summary for the store brand cookies. And that means we have to run the one variable statistics command 2 different times, one for list 1 and then once for list 2. So this is what it would look like: stat, and then calc, and then one variable statistics, the first option there. All right, on my calculator, it just leaves a blank. On yours, you might have a menu. So if you don't see L1 for the list or the X list, then you want to put in L1. And then the frequency list would be just 1, and then go ahead and calculate. All right, so we get the normal things like the mean, and today we'll talk about the standard deviation. You can see that there are 21 chocolate chips there, but that arrow is where you want to go. So go down further, and it's going to list the 5-number summary together. There's the min, there's Q1, the median, Q3, and the max. So I'm going to write down these numbers down here for Keebler. The min is 20, Q1 is 21.5, and then the median is 25, and the third quartile 28, and then finally the max is 33. So there's the 5-number summary for Keebler. And then for the store brand, remember that if you did the same thing that I did, I put those store brand cookies into L2. So when I run the one variable statistics, I have to change my X list to L2. And then it'll calculate the same one variable statistics for the store brand. There's the mean, standard deviation, and then we'll scroll down to get the 5-number summary. So 16 is the min, and Q1, and median, and Q3, and max, the 5-number summary. So 16, 21, 24, 27.5, and 33. All right, I probably should do one of these by hand as well. So I'm going to do one of these by hand. I'm going to go into my lists, and I'm going to sort one of them. So I'm going to sort list 2 in ascending order. And when I go to the list again, notice that all of those numbers are sorted. So I'm going to write them all down: 20, 20, 21, 21, 21, 22, 23, 24, 24, 24, 25, 25, 26, 28, 3 more 28s, 29, 31, 32, and 33. Now, hopefully I have all 21 there. I'm just going to quickly count: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. All right, so they're all there. Now, here's how you calculate the 5-number summary when all the data are sorted. A couple of them are easy. A couple sometimes can be tricky. Well, first of all, the first one, the lowest one, that's the min. So we know that. That's the lowest data value. And up here at 33, that's the max. And then you have 21 values. And so the middle one would be the 11th. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the lower, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the lower. So these are 10 values, and these are 10 values, And there's the middle one. So the middle one is what we call the median. Now, the first quartile is the median of the lower half of the data. Because when we do these quartiles, remember they're 25 percentiles. And so 25% of the data would fall in the lowest quadrant, and then the next 25% here, and then the next 25%, and then the next 25%. So when we establish these quartiles, we're dividing up the entire data set into 25% chunks, 25% of the data in 4 different chunks. All right, now we've already used the median here, so we're not going to use it again. So that means we have 10 values here. 10 is an even number. So if you wanted to calculate the median, you have to go and take the average of the middle 2. 1, 2, 3, 4. So right here would be the average of the middle 2. We'd have 2 values that are in the middle. And the number that goes right between 21 and 22 is 21.5. So the first quartile is 21.5. And then as you come down here, again, you have 10 data values. So you're going to break them up into 5 and 5, 3, 4, 5. So right there's the middle, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. The median of the upper half of the data is Q3. And the number that's between 28 and 28 is 28. So the min is 20. The min is 20. The first quartile is 21.5. By calculator, the first quartile is 21.5. By hand, the median was 25. By calculator, the median is 25. So all these numbers should line up. Q3 in the max, Q3 in the max. So this is how you do it by hand. And what you have is 25% of the data here, 25% of the data here, 25% of the data, and 25% of the data as best we can do. And that's what quartiles do. They divide all of the data up into chunks of 25%. Okay, now it's time to construct the bar graphs, or the box plots. If you look at these numbers, the lowest number is 16 and the highest number is 33. So we just have to make sure that our scale goes from, now maybe I'll just start at 16 and then jump by 2s, 18, 20, 22, 24, 26, 28, 30, 32, and 34. Okay, I've got a uniform scale now. All right, I'm going to put a dot on an imaginary horizontal line that represents each one of those 5 numbers. So 20, 21.5, well, there's 21, and 21.5 would be about right there. 25 would be about right here, 28 here, and finally 33 here. Now I tried to draw those points. They're just kind of reference points, but I tried to draw them so that they were all on kind of the same level, the same horizontal line. Now remember, we want a box in the middle, and then a whisker on the right, and a whisker on the left. So here's how we're going to construct it from our 4 points. The middle 3 points make up the box. So I'm going to draw some vertical lines through those 3 middle points and try to construct something that looks like a box. And then from the middle of the box out to the maximum, that's going to be the 1 whisker on the right. And then from the middle of the box out to the whisker on the left, or out to the minimum on the left, that's going to be the other. Now this is a box plot. It plots quartiles. Let's see how the store brand version compares. And we're going to draw them on the same axis. So maybe I'll draw with a different color this time. 16 and 21 and 24 and 27.5 and still 33. So for this box, again, I'm going to put 3 vertical lines through the middle to construct the box, and then a whisker to the left and a whisker to the right. And there we have our side-by-side box plots. And so we can compare the cookies, and we can say, you know, it looks like, you know, you could end up with some cookies that don't have a whole lot of chocolate chips in them. But in terms of the maximum, they have the same amount in the maximum, and these boxes are just slightly shifted over from one another. So it doesn't look like the store brand cookies have a significantly lower number of chocolate chips. maybe a little bit, but it's not really significant. So the calculator constructs a box plot, and you can do it by hand. Just to remind you, when you want to create a graph on your graphing calculator, we already have the data in. And if you want to construct a statistical plot, you have to go up here. This is the same place where we constructed the scatter plots. This is the same place where we constructed the histogram. The box plot is one other graph that we have. So I'm going to go up, second, and there. I'm going to turn two plots on now. I'm going to turn the first plot on, and I'm going to select this icon here, which is the box plot. And the first plot is going to correspond to L1, and then the frequency is 1. All right, now I'm going to go back to the stat plot. 1 is already turned on, and I'm going to go down to number 2. And number 2, when I go inside that one, I'm going to turn it on by hitting enter, and I'm going to select a box plot for that one as well. But my X list, I don't want to graph L1 again, so I'm going to change this to L2. So there it is. I hit Y equals, and you can see I have 2 plots highlighted now, and that means 2 plots are turned on. Now, if you wanted to set your window up, you'd want to make sure that you went from 16 to 34. But the calculator, if you do the zoom 9, hit the zoom key here, and then the number 9, it draws them for you. So you can compare the way that the calculator draws this to the way my graph looks. Very similar. And the beauty of this is if you put the data in the graphing calculator, if you hit the trace key here, guess where it's going to trace? Okay, right here. It starts at the median. If you go to the left, it gives you Q1. If you go all the way to the left, it gives you the min. Min, Q1, median, Q3, max. And you can jump to the other curve by using the up arrow, and then you can trace on the 5-number summary as well, right on the box plot. Today we're going to continue with stats. Last time we looked at the mean, median, and mode, the measures of center. And the measures of center are not sufficient for us to describe a data set, so we need something else. And the other thing that we typically look at is the dispersion in the data. Are they spread out, or are they all very close together? If they're all very close together, we would call them homogeneous. They're all alike in some way. And if they're widely dispersed, we can, maybe call that heterogeneous. The other thing we're going to be on the lookout for are data values that are very, very extreme. And we'll have a way to identify these extreme values that we call outliers. So most of the time when we calculate these measures of spread, there's the range, the standard deviation, you may have heard this term before, and the variance. And the variance and the standard deviation are very, very closely related. But those are the 3 measures of spread, dispersion, that we typically calculate in a statistics class. The formulas are very complicated, and so we normally allow the technology to calculate the standard deviation and the variance for us. And the only time we would ever calculate this is if we had some very nice numbers and it was a small number of data values. Otherwise, the calculation is too difficult. In statistics, we have a population generally. And if you're doing a study in the United States or a survey, then the population might be all US adults. But when we want to know something about the population, we usually don't ask the entire population. We do it once every 10 years, like this year, where we contact everybody and we do a nationwide survey, and it's called a census. But other than that, we get all of our results and statistics from a very small sample. So we might have a population, an adult population in the United States of 250 million adults. But when we do a survey or we want to say something about that population, we usually just look at a very, very tiny subgroup of the population. We call that a sample. And then sometimes the sample only has to be about 1,000. So because we have these two groups, the population, the big group, and then the small sample group, it turns out that the standard deviations that we calculate are different depending upon whether you're talking about the population or whether you're talking about the sample. The formulas are very, very close, but slightly different. So this is the variance, and this is the formula that we use for the sample variance. Notice the variable that we use is S. Our calculator is going to use SX, saying that this is the standard deviation of the variable X, and the standard deviation is the S here. And if we can calculate the variance to get the standard deviation, all we do is take the square root of the variance. All right, so we have the population variance and the population standard deviation here. And the standard deviation is, again, same thing over here. These are the population, we call them parameters, and these are the sample statistics. Usually we don't have all the population data, so usually we're just always just calculating the sample standard deviation. So that number gives us a sense of how spread out the data are. Now it's hard to know that if the standard deviation is 14, what that means, but because the data, it has to be understood in the context of the data. So 14 would be a small standard deviation if you're talking about these numbers that range from, well, 14 would be a small standard deviation for big data sets that are widely, where there's a lot of variation in the data. But what you should be able to do then is to compare two standard deviations. If one has a standard deviation of 5 and another data set has a standard deviation of 14, then what you know is the one with the larger standard deviation has the wider spread in the data. And the data set that has the smaller standard deviation, the other statistic that we have that describes the spread in the data is just a subtraction. If you take the largest data value, which is the maximum, and you subtract the smallest data value, which is the minimum, that's what we call the range. And it's the range or the span of the data values. How far is it from the smallest to the largest? Range. If you have a large range, that means the spread is wide. If you have a small range, then the distance between the max and the min is narrow. And like the mean, it's not very resistant to outliers. So if you have an extreme value, if you have data set right here, and then you have one extreme value that really takes you way over here, then the spread in the data is going to be much larger. And so the range is going to be much larger. So the range is influenced greatly by outliers. So here's a couple of other interpretations of the standard deviation. And generally, I think this is a good way to think about it. The standard deviation is small when the data values are clumped together, and the standard deviation is big when the data are greatly dispersed from one another. All right, let's take a look at an example. And here it is, miles per gallon. And it's a small data set. It's the MPG, miles per gallon for a Ford Fusion, 2013. And so they drove 6 of these vehicles, and they recorded the gas mileage, and this is what they came up with. You can see that from vehicle to vehicle, there's quite a lot of dispersion. Smallest MPG would be 23.6, and the largest one would be 37. So a couple of things we can identify here is that N is our sample size, 1, 2, 3, 4, 5, 6. The minimum data value is the smallest of these, and there are 6 data values, and the 23.6 is the smaller of the two. And the max, the largest one, is the 37.0. So one of the measures of dispersion that we can calculate is the range. And as I defined it earlier, the range is equal to the max minus the min. So the range in this case would be 37.0 minus 23.6. And the calculator doesn't calculate the range for you because it's just a subtraction. If you recall, it does give you the max and the min. And if you know the max and the min, you can do the subtraction yourself and calculate the range. So what is this, 3.4, 13.4? So that's quite a lot of variation in the gas mileage from the same car, right? Well, it's different, 6 different cars, but they're all the same thing. So that's quite a huge range. And the unit there would be mpg, miles per gallon. Okay, now if we're going to do something like calculate the standard deviation, we're going to use the technology to do that. And so let me show you how you enter this into the, all right, so we have range, sample variance, and sample standard deviation. Now, the calculator only gives us this one. So, and the variable that it uses for that is SX. In our formulas, we just call it S. So let's enter in these 6 data values into the calculator, and let's calculate the standard deviation. All right, here we go. So get your calculator out. It's what you should do on every one of these. If you see numerical data like this, you know the calculator is very powerful, and it can calculate data pretty quickly. The summary statistics pretty quickly. So 34, 33.2, 37, and so on. By the way, Excel does all this stuff too. So Excel has its own formulas. There's no one variable statistics command in Excel, but it has something else that it uses. All right, so once these are in, we're going to quit. We're going to go back to the home screen, and then we'll do the one variable statistics. So there's nothing new here because the one variable statistics command inside the stat menu, you edit to enter the data, and then you calculate the one variable statistics. It's the same function. It's not a new function. The one variable statistics gives us lots of summary statistics for the single variable. So I put my data in L1, so I'm going to enter in L1 here. If you're doing this with a menu calculator, then your X list or your list will be L1. Frequency would be 1, and then you calculate. So here's the mean. This is the middle. So the average of these numbers, that looks about right. And the standard deviation that you want is this number right here, the SX. So when it says find the sample standard deviation, that's the SX, and there it is. It gives it to you to up to what, 9 or 10 decimal places of accuracy, but generally when we report it out, we'll report maybe 3 decimal places. SX is equal to, and this is the sample standard deviation. If your book refers to just standard deviation, it's talking about this one. The other one would be the population standard deviation. And if you're looking for the population standard deviation, it's the sigma X, this one here. Okay, you see that? Sigma there, sigma X. So population standard deviation, sample standard deviation, SX. We're interested in the SX. All right, so approximately 5.13, I'll call it 4. All right, so we have the range calculated there, the standard deviation calculated there, and the last thing that they want is the sample variance. So if you look at this relationship here, the variance is this thing, and then the standard deviation is the square root of this thing. So if you want to go back the other way, and if you have the standard deviation, if you want the variance, you would just square it. Notice S is the standard deviation, S squared is the variance. So what we're going to do to get the sample variance, that's S squared, or SX squared, which is our 5.134 number squared. So take the standard deviation and square it. Again, this is a number that the calculator will not calculate for you because since they give you the standard deviation, they figure you could square it to get the variance if you need it. So I'm going to take that 5.13358 number and square it. So there's the variance, 26.35, whatever that number is. And I'll round that one to 2 decimal places. Now the variance does not have the same unit as the standard deviation because it's squared. So the unit would be whatever the unit of the standard deviation is squared. So I don't know what mpg squared means, but that's the unit of the variance. So here are the 3 numbers that they ask for in this problem. Range, we calculate by hand using the max and min. Sample variance we get from the calculator. sample standard deviation we get from the calculator, and sample variance we get by squaring the standard deviation. If you want the accurate answers, the best way to do it would be to use your calculator, because it does it quickly and it does it accurately. There is another function here that I showed you. It's in the list menu down here, which is above stat. So if you hit the second key and then list, and then you go over here to these math functions, and you can see number 7 down here. Number 7, it says standard deviation. And all you have to do is enter in the list name there. And here you can see it, standard deviation from one variable statistics, standard deviation by using a different calculator function. So depends on whether you just want one thing quickly, or if you want all of the summary statistics. Does this do let me check to see if this does variance. I don't see it there, but let me scroll down. Ah, there it is, variance. Variance of L1. And there you get that 26 number, 26.35 number. So I guess it'll calculate for you if you use this function, but it generally doesn't give it to you in the one variable statistics output. Okay, continuing on. See if you understand what standard deviation means. Here are 2 graphs. Which one has the higher standard deviation? Standard deviation has to do with spread in the data, how widely dispersed they are. The range also describes the spread in the data. So if you have 2 data sets, the one with the largest range is going to have the largest standard deviation. One with the smallest range generally will have the smaller standard deviation. So one thing we can do is we can calculate the range of each of these. So it looks like the high point is 60 and the low point is 40. If you take 60 minus 40, you get 20. So the range is 20 for that one. And in this one, the data values range from 30 to 75. So we would say the range is equal to 75 minus 30, or 45. So since this data set has the larger range, it's also going to have the larger standard deviation. So which histogram depicts a higher standard deviation? It's this one here, because it has a larger range. All right, and I'll just share this with you here. In a bell-shaped distribution like this one, you can estimate what the standard deviation is. The standard deviation is approximately equal to the range divided by 4, or range divided by 6, somewhere in there. But if you just want a ballpark, you can get a ballpark estimate of the standard deviation by just taking the range and dividing by 4, 5, 6, somewhere in there. But you have to have a distribution that's approximately bell-shaped. Okay, so now we're going to get into this. We're going to use the standard deviation to create a horizontal scale for a graph. So here's how it's going to be constructed. In the middle, we're going to put the mean. And then instead of creating a scale that jumps by 1s or jumps by 2s or jumps by 10s or something like that, the scale marking that we're going to put 3 scale markings out to the right and 3 scale markings out to the left. And the unit that we're going to use, the scale unit that we're going to use here to jump from the mean to the next scale marking and then to the next and to the next, we're going to use the standard deviation. So for example, if the mean is equal to, I'll use the variable mu, you can use the population mean or the sample mean. Let's say that it's equal to 16, and the standard deviation is equal to 2, and let's call this the population standard deviation. Then what we would do is we would put 16 right in the middle at the mean, and then our scale marking would be the 2, the standard deviation. So we would add 2 to get 18, add another 2 to get 20, and add another 2 to get 22. And those would be the 3 scale markings to the right. We would subtract the 2 once, twice, and 3 times to get the scale markings on the left. So in these problems, you're going to be given the mean and the standard deviation, and then you create a scale. Now there's a special kind of a bell-shaped curve called the normal curve, and it has certain properties. Many data sets you've seen are bell-shaped. Even if they're not bell-shaped, they're approximately bell-shaped like these. High in the middle, and then they taper off to the left and taper off to the right. High in the middle, taper off on both sides. We would say that these are bell-shaped or a new word for today is normal. And if you have a normal distribution, then the data conform to the following facts. All right, I'm just going to draw a bell-shaped curve here. So I'm going to go up to the high point there. And then by symmetry, I'm going to go up to about right here, and I have to go up to the same height over here. And then if I go over one more, put a point that high and an equal point, the same height over here, and then maybe another point close to the horizontal axis, 3 standard deviations away. So if you want to create this nice bell-shaped curve, this normal curve, then here's what you do. You make it kind of flat at the top, and you go concave down, so it's symmetric. And then as soon as it hits this first point, the concavity changes to concave up. And this is what the graph would look like. So it's bell-shaped, it's normal, and it has the scale that looks like this. Now here's what, and there's this empirical rule. And the empirical rule deals with normal curves like this. The empirical rule is sometimes referred to as the 68, 95, 99.7 rule. And there's so many different data sets out there that conform to the bell-shaped curve like this that they've studied it in a lot of detail. And so here's what they say. Here's what this means. Here's the mean. If you go 1 standard deviation to the left and 1 standard deviation to the right, in this range from 14 to 18, you're going to find 68% of all of the data values. So just imagine that you had a histogram like this. If you went out 1 standard deviation to the left and 1 standard deviation to the right, about 68% would fall in that middle area. 68% is a supermajority. It's more than 2/3. So in a bell-shaped distribution like this, everybody is close. A big chunk of the population is close to the middle. And you can tell by these other numbers what's going to happen. If we go out 2 standard deviations to the left, 1, 2, and hit 12, and we go out 2 standard deviations to the right, 18, 20, here, then what you're going to observe is that 95% of all the data values would be within 2 standard deviations. And similarly, if you go out 3 standard deviations, 1, 2, 3, and hit 10, or if you go 3 standard deviations to the right, 1, 2, 3, and hit 22, what you're going to find is that in a normal distribution, you're going to fully have 99.7. All but 0.3% of the outcomes will fall within 3 standard deviations. There is essentially no data values larger than 3 standard deviations away from the mean, or less than 3 standard deviations below the mean. So we would say something like this: 68% of the data fall between 14 and 18, okay? 68% fall between 14 and 18, a little bit. 95% of the data falls between, okay, so 12 and 20. And 99.7% of the data falls between 10 and 22. Now these numbers are going to change, these numbers here are going to change with every new problem, because the mean and the standard deviation are going to change from one problem to the next. These numbers here will not change. It's always going to be 68, 95, 99.7. And here's the graph on the handout. You can see they've done it just slightly different than me, and they've used mu and mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. But basically it's add 1, add 2, add 3 standard deviations to the right, subtract 1, subtract 2, and subtract 3 standard deviations to the left. You can also see in this graph they have more detail. They use the idea that there is symmetry. And so since 68 falls in this region, we have 34% here and 34% here. These are equal chunks. So you just split the 68 in half. And they give you the other percentages in there as well. If you add up these 4 percentages, 13.5%, 34, 13.5%, and 34, those 4 add up to the 95. But it's just a little bit more detailed in the graph that I drew. All right, let's look at an example here. So they're telling you that you're going to use that empirical rule, that bell-shaped curve that we just talked about. The SAT math scores have a bell-shaped distribution. All right, so here it gives us the mean of 515, and then here it gives us the standard deviation is 114. Now, because it said there was a bell-shaped curve, we're going to draw that bell-shaped curve with the mean here, right in the middle. So right in the middle is 515. They gave us what the mean was. And then we're going to jump by 114. So our scale marking now is 114. This is our sigma. So I'm going to add 114 once, twice, 3 times. So 629, 743, and 837. And then I'm going to subtract the 114 once, twice, 3 times. It's always 3 scale markings to the left and 3 scale markings to the right, 287 and 173. 68% fall within 1 standard deviation, 95% fall within 2 standard deviations, and 99.7 fall within 3 standard deviations. All right, so let's answer these questions. Go ahead and put your answers in the chat. I want to make sure that you're picking this up. Part A, what percentage? So you're going to give me a percent answer. 73% or something like that. All right, between 401 and 629. 401 and 629, right there are those values on our scale. So what percent of the data, if this is a bell-shaped curve with a mean of 515 and standard deviation of 114, what percentage of the outcomes would fall from here to here in this range? Answer, 68%. If the mean is here and we go 1 mark to the left, 1 standard deviation and 1 standard deviation to the right, the rule says that if we go 1 standard deviation to the left and 1 to the right, and we want to know what percentage of the data values fall between 14 and 18, it's always in a bell-shaped distribution going to be 68%. The answer is going to be 68% every single time. If you're working in a normal distribution like this and you go if you go 2 standard deviations away from the mean, 2 of these markers, 1, 2, 1, 2, then 95% of the data would fall in that range. What's the answer to part B? It says what percentage of the scores is less than 401 or greater than 629? So let me just add this, that there's 100% of all the outcomes fall underneath the curve. So if you have 68% here, part B just says, well, what's everything else? Because the 68 falls within here. And in this problem, it said, well, what's the rest of it? So if there's 68 in here, then that must mean there's 100% minus 68%, 32%. Now, for this next one, you might want to break it down a little further into these percentages. I don't know if you can read them, but I'll translate them over to the next graph. In this one here, you have 34% between these two numbers, 34% here, 13.5. 13.5, and as you go out 1 more, this is 2.35%, and this is 0.15%, all of the data going that way. This is 2.35%, and then there's 0.15% going all the way over there. All right, so in part C, it says, and you can put your answer in the chat again, what percentage of the SAT scores is greater than 743? So I'm going to look on my scale, and I see 743 right here. So we're looking at all of those. What percentage of the outcomes would be greater than 743? Yeah, you just take these two and add them together. 2.35% would be the number of, or the percentage of the data values in this range. And then from here on over, it's 0.15%, the empirical rule. Okay, so now we're back to looking at, again, the meaning of the standard deviation. So we're going to work through a couple of examples here, and all of this goes together. So here are, if you can look at the rows here, row 1, row 2, row 3, row 4, and they give them Roman numerals. So match the Roman numerals to the graphs. Which graph has a mean of 53, a median of 53, and a standard deviation of 1.8? they get tricky because of the 4 different graphs, 3 of them, graph 1, graph 3, and graph 4, they all have the same mean and median. The only one that has the different mean and median is the second one. So maybe that's the easiest one to figure out. Remember that the median and the mean in a bell-shaped distribution will be in the center. And that's why they're called measures of center. So focus in on the center of the data distribution. What's in the middle there? Is there one where 60 is the middle? Okay, so next to graph A. Okay, so let's answer. Well, let's identify which one is graph number 2 first. So go ahead in the chat and select A, B, C, or D that corresponds to the graph of 2. Which one is it? Which one is 2? Draw at the center. All right, so I'm just going to draw a vertical line through each one of these graphs where I think the center is. I think the center of this one is about right here in the middle. I think the center of this one is probably right here. The center of this one, well, there's more data values over here, so maybe it's kind of in here somewhere. And the center of this one, maybe right here. 3 of these have a median of a mean and median of 53, and the 4th one has a mean of 60. So the only one that comes close to a middle of 60, based on how I have them drawn here, this one would be about 53, somewhere between 52 and 54. This one is close to 52, 53. This one here, close to 52 or 53. And this is the only one where this is 52, this is 62, and the line is much closer to 62. So this is the only one that's feasible to have a center of 60. So I'm going to say that this graph right here is number 2, and we'll cross that one out. All right, now the next one, they get a little trickier because now we need to focus on the standard deviation. Now we've already gotten rid of that one. We've already identified that graph. So here's one with graph number 1 has a very small standard deviation. So those data values will be very clumped together. They'll be very, within a very small range. Then you compare that to 10. Well, 10 is a standard deviation that's 5 times as large as the 1.8. Then you have a standard deviation that's 22. And that means, all right, so 1.8, 10, and then 22. The larger the standard deviation, the more widely dispersed the data are. So if you're going to identify, because all 3 of these graphs here have the same middle, 53. So now we're focusing on the spread. Okay, so which one has the smallest? Go assign number 1 to A, B, C, or D. So put your answer to graph number 1 in the chat. A, B, C, or D. You're all answering B. And I agree. So if you look at just kind of say 48 and 56, if you just do the subtraction there, you get 8. And if you divide that by 4, you get 2. So remember how I said, if you take the range and divide by 4, you get something close to the standard deviation. And 2 is close to 1.8. Let me do this one. 123 to, I don't know, this might be 13. Oops. So if we take the max, 123, the largest data value, and then subtract the min, 13, and divide by 4, well, that's 110 divided by 4, and that's about 23, 27. All right, anyways, it's up in the 20s. So the only graph that even comes possibly close to this is the one with the standard deviation of 22. So this is going to be 4. And I think we've already identified this one to be 1. And this one here has a standard deviation of 10. So if you take 82 and subtract 32, you get 50. And if you divide by 4, 12.5, it's in the ballpark, close to 10. So graph 3 would be this one. All right, so I know it's a new concept, and you've got 2 different numbers you're working with. The mean just gives you the middle value. The standard deviation gives you the spread. And it's hard to understand the spread if you just look at a single data set. But if you compare different data sets, the data set with the smallest standard deviation will have the data values that are closest together. How do you tell if they're closest together? Well, just look at the difference between the max and the min. Because the ranges will get bigger as the standard deviation gets bigger. All right, we'll come back to some more examples in that if we have time. Otherwise, I'll put these together in the notes. All right, continuing on, we have this other statistic that we call a z-score, And the z-score is a number. We use numbers all the time in math. We use the m. M is a number. That means the slope of a line. And if we know what that number is, we kind of have a sense of what the line looks like. We know how steep the line is. So one number is associated with something on a graph. Remember R, the correlation coefficient? That told us something about an entire data set. If R was 0.9 or 1, close to 1, then we know that the scatter plot would look, something like this with very little variation off this upward trend. R equals 0.9. So we use some variables like this, and they have some meaning. R tells us about the strength of the linear relationship. M, the slope, tells us about the steepness of the graph. The z-score is similar to that. But here's what the z-score tells us. It tells us the number of standard deviations away from the mean. So if the standard deviation is a large number, a large positive number, then we would say that the data value in question is extremely large, several standard deviations above the mean. So it's a very, very extremely high value. If the z-score is negative, then we say that the data value is less than the mean. So positive z values mean the data value is above the mean, and there's a z-score that corresponds to every data value. And the data value in the formula is the x. It appears whether you're using the sample mean and sample standard deviation, or if you're using the population mean and the population standard deviation. The z-score tells us how many standard deviations we are from the mean. Do you remember this example? So here's a z-score question. What is the z-score of 20? So imagine that there's a data value out there, 20. It's one of our data values, and we want to know what its z-score is. A z-score tells us about the position. So we're going to use our z-score formula. We're going to take the data value, which is 20 in this case, subtract the mean, and then divide by the standard deviation. The formula on the other page, it looked like this: x minus mu divided by sigma. Now I'm going back to this example because we do know what the mean and the standard deviation are. You need those two numbers in order to calculate the z-score. So let's take our data value of 20, our mean of 16, and our standard deviation of 2, and let's plug them all in to this formula. If you do that, you're going to have 20, that's the x value, the data value, minus the mean, which is 16, and then we're going to divide by the standard deviation, 2. So you get 4 on top, 2 on the bottom, and that gives you a 2. Here's the middle. 18 is 1 standard deviation above the mean, and 20 is 2 standard deviations above the mean. So when we write down the data value 20, we can see on this graph that it's 1, 2 standard deviations above the mean. The z-score will calculate that number for us, even if we're dealing with messy numbers. What's the z-score of 10? In the chat, please, without using the formula. What's the z-score of 10 in this problem? Let me give you the definition again. The z-score is the number of standard deviations a data value falls from the mean. So to answer this question, you have to ask yourself, How many standard deviations is 10 away from our mean of 16? 1, 2, 3. But it's 3 below the mean. So yes. No. So you see you were right the first time. Negative because it was less than the mean. So if you want the z-scores and you want to put them on the same scale, this is 0, 1 standard deviation, 2 standard deviations, 3 standard deviations above the mean, 1 standard deviation below, 2 standard deviations below, and 3 standard deviations below. All right, let me turn it around on you. And if the z-score is negative 1.5, what's the data value? In this example, write your answer in the chat. See if you can figure that out. We're going backwards now. Okay. You either see it or you don't. So the first thing we're going to do is we're going to locate the z-score of negative 1.5. That means 1.5 standard deviations below the mean. So what data value in this context would be right there? Yeah, it's somewhere between 12 and 14. In fact, it's right between 12 and 14. So the answer would be 13. But in order to answer the question, I mean, it's certainly nice to have this scale. All right, so that's a z-score. Now, what can z-scores do for us? Let's look at an example. It enables us to answer the question when we're comparing apples to oranges. And you can see an application here in professional baseball. Clayton Kershaw, who used to play right here in town in Midland, by the way, for the Great Lakes Loons. He's now, I think he was a award-winning pitcher, Cy Young Award maybe. He had the lowest earned run average at the mean number of runs given up for 9 innings of innings pitched. But he played for the National League. Okay, so his data value is 1.77. This was his earned run average. In 2014, Felix Hernandez of Seattle had a lowest ERA in the, this is the National League, and then he was in the American League. And he had the lowest ERA of any starting pitcher in the American League, and his data value was 2.14. So when you look at those earned run averages, you might say, oh, this one has a lower earned run average, so therefore it's better. And so therefore Kershaw must be the better pitcher. However, there might be better batters in the American League. And so that might force up. And you know the American League has a designated hitter, so they're going to give away more runs generally because they've got a good hitter in place of a weak hitter, the pitcher. All right, read further. In the National League, the mean is 3.43, and the standard deviation was 0.721. Whereas in the American League, the mean was 3.598, and the standard deviation was 0.762. So what they're saying is that you really shouldn't just compare individual IRA or ERAs. You should actually look at how other pitchers in those leagues did as well, because the other pitchers in your same league were facing the same batters as you were. All right, so the way that we're going to determine which pitcher is the best is we're going to calculate a z-score for each one. So here, we're going to take the data value, subtract the mean, and divide by the standard deviation. We'll do the same thing for the American League pitcher, Felix Hernandez. Take his ERA, subtract it by the mean ERA, and divide by the standard deviation. And the one with the most negative z-score means that they have the most extreme score, which means the best score. The highest negative number would be the lowest ERA. So we'll calculate both of these. Remember to use parentheses when you have a subtraction on the top. So this one is negative 2.302, and the other one is negative 1.913. Now this z-score is further to the left. It's more negative. So it's more extreme, which means it's lower. And this is much lower. And so because this standard deviation is much lower, we're going to say that indeed Kershaw is the better pitcher.